Hey guys, hopefully you've done the worksheet. If you haven't, go do it and then come back here. Ready for your answers? Here we go. The answer to curveball number 1 is 2.1%. Curveball number 2, the pH goes down. The pOH also goes down. The solution is still neutral. Curveball 3, CH3NH2 is the stronger base. HCN is the stronger acid. Curveball 4, HNO2 is the answer to the first part, and pH should be 2. Curveball 5 should be 3, 1, 2. And curveball 6, acid, base, acid. All right, so now I'm going to go through every single one of those. If you got them all right, well done. Go to the head of the class. Hey, you know what? I'm going to give you imaginary Smarties. If you got them all right on your own, imaginary Smarties for you. Remember to wash your hands before and after pretending to eat them. So let's take a look at curveball number 1. So I need to calculate the percent ionization. This is a little bit different problem, but it's really not that different. Whenever you calculate the percent of anything, you need whatever the part is over the complete amount, over all of it. And then you take that and times 100. So I want percent ionization of a weak acid. It looks like, it's a weak base. So I want percent ionization of a weak base. So how much hydroxide am I going to make per amount of stuff that I have in total? So looks like my total here is going to be 0.10 molar. So that's my all. That's going to be my 0.10 molar. That's my all. And then I'm going to need to find whatever the part is that's ionized. And of course, the way we do that is with an ice table. So let's make a quick ice table. Our initial concentration of the methylamine is 0.10. I'm going to go ahead and write it up here, CH3NH2. And that's going to this is going to work a lot like ammonia. This NH2 works a lot like the NH3 of ammonia, and instead of a third hydrogen, it has a methyl group, a CH3 on there. So this is going to go CH3NH3 with a +1 charge. And again, if you don't know the name of that, if you can't figure out what that's going to be, that's fine. You know it's a base because he gave you Kb. So just put conjugate plus the hydroxide. So we're going to have none of this to start with. It's a regular ice table, regular equilibrium reaction. So this is going to be minus x, this is going to be plus x, this is going to be plus x. Right? We're not doing any multiples or anything like that. So this is 0.10 minus x, this is going to be x, and this is going to be x. And so that means my Kb is going to be equal to x squared over 0.10 minus x. Now, I know that I've got a small Kb, so that means I can ignore this x, right? So what we're saying here is 4.4, this is Kb, times 10 to the negative fourth. It's going to be equal to x squared over 0.10. So that's pretty easy math as far as that goes. I mean, the square root's going to be a bit, but we can solve that too. We're going to multiply both sides by 0.10. We take the square root of both sides, and we're going to find that x is equal to, looks like 2.1. Maybe we should not round it so much. 2.0976 times 10 to the negative third. So that x, that's our concentration of hydroxide. That's how much it's ionized, right? It's also the other ion. But so that x, right, that's how many of them are ionized. So percent ionization, it's this divided by that. So it's going to be 2.0976 times 10 to the negative third over 0.10. Actually, what that's going to make is 2.0976. So let's just call it 2.1. So the answer is 2.1, and that's a percent, so 2.1%. All right, let's look at curveball number 2. The auto-ionization of water is endothermic, and we did talk about this in class when I first discovered this problem because it was kind of interesting. I don't know if you remembered it. It seems like a long time ago now. But if it's endothermic, the auto-ionization of water, so water reacting with itself to make these two things, right? We know that these two things occur in distilled water in equal amounts with a concentration of 10 to the negative 7th, right? That's why we have pH of 7. But what's going to happen to the pH as the temperature of water is increased if this reaction is endothermic. Now, remember when we talked about Le Chatelier, we can think of heat as one of the reactants or products for endothermic or exothermic reactions. So this one's endothermic, so we think of heat as, hopefully you remember, as a reactant, because as we add heat, it's going to drive the reaction towards the right. So we raise the temperature, it's going to drive our reaction towards the right. And we're going to get more ionization, which means we're going to get more concentration of hydronium. We're also going to get more concentration of hydroxide, which means the pH, yes, it's going to go down because that's what happens when you increase hydronium, but the pOH is also going to go down because we're going to increase the concentration of hydroxide as well. So the pH of the water goes down. The pOH of the water goes down. And the solution, because they both go down, it doesn't become acidic when the pH goes down. It doesn't become basic when the pOH goes down, because they go down in exactly the same amount when we raise the temperature. So, of course, the solution remains neutral. Now, it's interesting because pH and pOH, we know they're supposed to add up to 14, but at like 60 degrees Celsius, the pH is 6.5, not 7, and the pOH is also 6.5, not 7. So the pH and the pOH add up to 13 instead of adding up to 14. And if you raise the temperature, that would change even more. Here's curveball number 3. So this is an interesting problem because we have a weak acid and a weak base reacting together. It's an equilibrium reaction, and so we have a weak acid and a weak base on both sides. So let's identify which is which, because we have to figure out which acid is stronger and which base is stronger. We need to know which ones are acids and which ones are bases. So this one can't give a hydrogen, so that's got to be a base. And actually, we know that's the conjugate base of this acid. So, and again, this is weak, weak. They're all weak here. So if this is a base, this must be the acid, and I can see that it has an extra hydrogen, so this must be the base. So I've got an acid and a base on both sides. And we look at Kc here. Now remember, when K is less than 1, that means that the reactants are favored in the reaction. So this reaction is going mostly to the left, right? It's going mostly that way. So towards these guys. So we want to remember hydrogens will go to the stronger base. And I don't know if you remember, but when we talked about strong acids like hydrochloric acid, the reason that's such a strong acid is because the chloride ion is actually a weaker base than water. So the hydrogen will leave the chloride ion to go to just plain water to make it the hydronium. So, and that's what makes that such a strong acid, is that chloride ion is so negligible as a base. So the hydrogen ion always goes to the stronger base. So since this reaction is going to the left, the hydrogen ion is stuck to the stronger base on the left. And that means that this hydrogen ion, right, that hydrogen is on this, which means this is the stronger of these two bases. Of these two bases, right, cyanide ion and methylamine here on the right, of those two bases, the methylamine, the CH3 and H2, has to be the stronger base. So which base is stronger? CH3 and H2, because, in H2. So if this is the stronger base, then this must be the weaker base, which means that this must be the stronger acid. So HCN is the stronger acid. It makes sense too, because the stronger acid is going to really want to get rid of that proton more than the other guy. So it's going to give that proton. And when it gives its proton, this reaction goes to the left. So that also drives this reaction to the left. And those two things are what's making Kc less than 1, which makes this reaction go to the left. So these are the two answers to this one. Curveball number 4, try this with no calculator. This is actually kind of based on a multiple choice question that I've seen, in which, of course, you wouldn't get to use a calculator. So I've got nitrous acid. It's got this little bitty Ka. Since it's got a little bitty Ka, I know which of these three is going to be most concentrated, right? Because these two are going to be formed. My reaction is this. HNO2 reacts to form NO2 minus plus H3O. But this is a weak acid. And I know it's a weak acid because it's got a teeny tiny little Ka. And that means most of it is staying like this because that Ka is so small, which means that this is the right answer for which one is most concentrated in this solution. No problem there. But we also need to find out what the pH would be. And so for that, we're going to need an ice table. Now, you may be thinking, ice table with no calculator, no worries, you'll be fine. So here's my ice table. I'll go ahead and use this equation that I wrote out here. Starting with 0.25 molar of this nitrous acid, none of this and none of this. I'm going to lose some of this, form some of this, form some of this. So this is going to be 0.25 minus x. This is x, and this is x. And again, this is small, so I can get rid of that x. So this is basically Ka is going to be equal to, well, I'll put this value here, 4.0 times 10 to the negative fourth. And that equals x squared products over reactants, which is 0.25. And like I said, I can get rid of that negative x. Now, when you start solving this, you can see pretty quickly, I'm going to multiply both sides by 0.25. That's going to give me 1.0 times 10 to the negative fourth. Then I have to take the square root of that to get my x. And that's easy to do. All you have to do is make that a 2. So it's going to be, basically it's this, it's 0.01, right? 1 times 10 to the negative second. So the correct answer to this is 0.01, but that's not a pH, right? I need to find the negative log of the concentration. That's the concentration. That's my X. That's the concentration of hydronium. So what's the negative log of 0.01? And so 1 times 10 to the negative, 10 to the negative 2. That's my pH right there. When this is a 1, that's your pH. So this is a pH of 2. So there's our answer. Looking at curveball number 5. Number the following solutions in order from lowest to highest buffer capacities. Which one of each of these pairs can handle more addition of acid or more addition of base? And so all you got to really do here is look at the concentrations, and that's going to tell you which has the greater buffer capacity. So since it says number 1 should be the lowest, number 1 is going to be the one with the smallest values, and that's this one here. So that's the lowest. Looks like this is the highest, so they'll call that. And this one can buffer a little more acid than it can base, but still, it's both are less than the first one there. So 3, 1, 2 is your answer for curveball number 5. Not too bad, like I said, it's just based on concentration. The greater the concentration of the buffer, the more acid or base it can neutralize. So for curveball number 6, for each of the following buffer solutions, determine whether it has a higher capacity for neutralizing acid or base. And it's the same thing. So if you got a lot of base, it can neutralize more acid. If you got a lot more acid, it can neutralize base. Remember, in a buffer solution, you're always going to have an acid and its conjugate base, or a base and its conjugate acid. Either way, they're conjugates of each other. So let's look at this first one. I've got acetate here, and I've got acetic acid. Now be careful because I got 2 of these. So this is actually, when it comes to the acetate, I've actually got 0.006 molar of the acetate, whereas this is only 0.004 moles of acetic acid. So this has got more acetate. It's got more conjugate base, so it can neutralize more acid. The second one here, it looks like I've got 0.015 molar of this guy and 0.003 molar of this guy. So it looks like the guy on the left here, this NH4Cl, has another hydrogen, which means I passed a hydrogen over there. So that's my conjugate acid to this base. So it looks like I've got more conjugate acid than I do base. That means it can neutralize more base because it's got more acid. And then this last one, I've got an acid here, and I know that because it starts with an H. We've got that same guy here stuck to a potassium. So this is my conjugate base. This is my acid. And it looks like I've got more of the base, which means I can neutralize a little bit more acid than I can base. So you might see this question where it says capacity for neutralizing. And you're just looking to see if it has more base, it can neutralize more acid. If it has more acid, it can neutralize more base, and that's not too bad. So that's all those curveball questions. Hopefully you did well on them. I'll see you guys next time.